Okay, today we're going to talk about stacks, which actually have a lot to do with recursion. So far we actually have talked about a stack. What is a stack? Memory. What's special about the stack in memory?
Isn't that where things get allocated?
What things?
Variables?
What type of variables?
Static variables?
Okay, maybe. Well, stack variables are usually in the static memory.
Right, I knew that. That's
Yeah. You're just testing me, right?
Just
You're trying to see I knew what was going on. Oh, all right, good.
why.
So when you create an object, where is that allocated?
Static. No, it's on the static. Heap.
Heap. There we go.
How do you go?
Whoa, man.
It's a rough one.
Maybe, yeah, been a while. So if static variables are in the static memory, new objects are in the heap, what could possibly be on the stack?
Functions.
Sure, yes, functions. There we go. Functions and their local variables. But just to help you get a little more confused in computer science, a stack can also refer to a data structure, which is the last in, first out. So this is thinking, just like a stack of plates, except for you can only put one plate at a time or manipulate one. So you can only take the top plate off or put a plate on top. It's probably the easiest way to think about it. Anything can be added to the stack and it goes on the top. Anything removed is taken off the top. Well, we're just going to be doing a lot of whatever this technique's called, where the sentences get slowly moved out on the board. And so things are removed in reverse order from that which they were inserted. Why is that? Let's go draw it. Y'all like drawings, right?
Yeah.
Let's do it in a diagram. No, what does this look like? With the stuff?
Right.
So this over here represents this over here. If you want to find out how, take data structures. But this is a matrix. See? Rows, columns. Okay, good. All right. So if we're in a computer, we're not adding plates. We're probably adding numbers. So if we add, give me a number.
1.
Beautiful number. So we add 1 to the stack. Let's add another number.
0.
0. Ooh, being tricky, eh?
1. Isn't that what it's just going to be 1 from zeros, right? So.
Let's get something
All right.
a little different.
40.
40. All right. And the top of the stack's right there. So if I were to remove an item from the stack, I would remove the top, and that would be 40. My eraser. Ooh, that's right over the glare. Then I would remove the.
1.
Then I'd remove the 0, and then I'd remove the. So is that in the reverse order that we put it on? Why is that?
Top. Down.
Yeah, well, it's the way the stack works,
Yeah.
right? You're always manipulating the top. So it's a last in, first out, because the last item you put in will be the first one to come out. All right. Constructing a stack. Well, could we use an array or a linked list to construct a stack? Sure. Or we could just use Java's stack object. Which would y'all prefer?
Stack.
The stack object? Okay, all right. Well, I guess for today we'll use the stack object. So stack equals new stack. See, we'll go over here. And right click, new, jump class, stack, fun, because always fun using stacks. Public static void main string args. All right, now I'm going to make sure everything is really confusing. Make a stack of integers. I'll call it stack equal to a new stack. And we need to Alt-Enter to import that. Notice that I imported it up there, and now we're good to go. All right. Can someone tell me what this line of code is doing?
Making a stack of integers on the heap.
On the heap, okay. Good start. That's what the new stack does.
Oh yes, you're making a pointer.
Right, so the pointer is called stack, and it resides on the no, the object's on the heap. Right, so we have a pointer called stack, resides on the stack, and it points to a heap, right. Everyone got that? Yeah. I know it's confusing, but that's what's going on. All right. So let's go ahead and use the stack we created. Let's do for int, ooh, that's an interesting open parentheses, int I equals 0, I is less than 100, I plus plus. We'll do stack.push of new integer sub I. All right. And then we're going to go int, it did it again. Actually, we won't do it that way. So we can push integers onto the stack. All right. If you want to pop them all, you can just do while not stack dot is empty. While it's not empty, we'll just print them out.
You say pop?
Yeah, you pop the stack. You push on the stack and you pop. So pushing is adding, popping is removing. So you just push and pop. And then you can ask if it's empty. So what should I print out here? What should be printed out here?
No, 99%.
There you go, 9930. All right. Any questions on that? I'll make it a separate function. Simple stack example. And we'll go up here and cut that code and put it down here. And then we'll just call it for the fun of it. Excellent. All right. So you can push an object that puts it onto the stack. You can do stack.pop, which is going to remove the object at the top of the stack and returns it. You can do .peek, which just looks at the top of the stack without actually removing it. So you have push, pop, and peek. And then you can ask if it's empty. And you can actually search for an object on a stack, but this really makes no sense, so please never do that. So what do you think a stack is useful for? Don't want to use an array or a list. Okay. There's actually a lot of problems that a stack simplifies. Any sort of nesting, such as parentheses? Well, we're just going to talk about it. So anytime you're doing nesting or you're doing any type of arithmetic expressions, it'll help a lot. It's used internally, we've already talked about. Your computer's using a stack to implement your functions and your function calls. Now, recursion uses the internal stack of your computer, and that's why I'm actually having y'all go through a stack right now with recursion, so you can hopefully see that they're very similar in a way. It's just that when you call function, you're pushing new local variables of the function on the stack, and then when you return, you're popping off the stack. Keeping track of previous choices, backtracking. Did we do a maze example? Okay, great. So you could have also implemented that with using a stack instead of recursively. Right. Keeping track of choices again. So for example, here's a good example. When you are writing your code, your compiler needs to know if all your parentheses are balanced, and therefore your code will make at least some semantic sense. So basically you want to make sure that whenever you close something, the next item over should be the opening of it. Notice you can open, and then we can close this parentheses, and this curly bracket needs to match that curly bracket because this was already balanced. And then you put two curly brackets around it, now that is balanced. Keep going on, you have solid, another balanced parentheses, and then another solid. Those two are balanced because you have something balanced in between. And then here you have this open parentheses balanced with this, this closed parentheses balanced with that open parentheses, and then finally that closed parentheses balanced with that last open parentheses. You'll see that this is something the computer has to do in order to compute your code. Why is the one on the right not balanced?
Because there's a closed parenthesis in the brackets on the right side.
Yeah, so if you go over here, this closed parentheses would try and match with the solid open, and that makes no sense. So this is not balanced. How would you try and solve this?
Don't you just move it over?
Oh, no, you're detecting the compile. I mean, I understand what you're saying, right? You could fix it by moving it over. But how could the computer figure out if your code is balanced or not? A stack. Why can't we do something else?
You can iterate through it, right?
Well, simply counting is not enough because you could try and count the number of open and number of closed. But that's actually not going to tell you if they're balanced. Because just in that example, you have the right number of open and closed, but it's still not balanced. So a really simple way to do this, you can do it with the stack going left to right. If you see a open parenthesis, open solid bracket, open curly, push it on the stack. And you see it close, pop the stack and check whether you got the corresponding open or closed parentheses. And then that'll basically tell you if you're actually balanced or not. When you're at the end, check that it's empty. All right, let's go do that. We'll create a little function, public static boolean. Boolean is balanced string. What do I want to call this? We'll call it expression. And we'll go over here. System.out.println is balanced. Whoops. Balanced. And so that should be balanced, right? So we want that to return true. Let's go back over here. Is balanced with an expression. So we're going to first create a stack. Let's see. What are we going to call tokens? All right. For int I equals 0, I is less than xpr.length, because what we need to do now is actually iterate through the string. So we'll go ahead and charchar, let's see, c equals xpr.char at index, so that'll get the character at that index. So we'll do a quick little switch statement on C. And if C, in the case that C is if it's an open parentheses, case that it's a open solid bracket, and in case that it's an open curly bracket, we'll just do stack.push on C, right? Or tokens.push. So if it's one of the open ones, we're just going to push it. And I made it of integers, which is silly, because it's really characters. I misspelled character. I guess character only has one A. There we go. Let's go ahead and break out of that. Why is this going to work for all three of those? Did y'all do switch statements? Mm-hmm. So why would this work for each of those three? Oh. So in a switch statement, just trying to make sure there's that fall through, or if you don't have a break, it's going to fall through to the next one. So that's why those three work. Now, we're going to have also 3 cases for the close. And before I implement those, I do like to put up my default, and we'll just have it system.out.println unknown character, and we'll go and print out the character. And then we'll just return false. Okay, so we're going to push it up here, and we're just going to say that if it gets through everything, we did not detect an error, so return true. Okay, so this pushes it on there. If it's a curly bracket, what do we need to do? We need to, well, we need to go, we actually just need to test if tokens.pop equals, what does it need to equal? If we're at a close parentheses, what needs to be popped off the stack at this point? An open parentheses, right. But we're only testing to make sure that it's balanced, so if it doesn't equal that, then it's not balanced and we'll return false, right? Okay, let's go ahead and break. And the next 2 are essentially the same. We're just going to do it for the curly and the other one, and the curly and the solid brackets. Okay. Any questions what I've done here? Nothing yet? Okay. Let's run it, see what happens. Ooh, there's an error. Where's the error? Oh, it's not a new string, it's a new stack. There we go. True. All right. Looking good. But if I were to do this, would that be balanced? No, so that should be false. False. Okay. Let's take one of these and run through it on the board just to clarify what's happening. Which one do you want? The first or the second one?
First one.
The first one. All right, what do we got? We have parentheses, solid brackets, parentheses, solid brackets, close parentheses. Great. Okay. So I wrote the expression up here. We'll start our stack down here. Beautiful. Nice and squeaky. What gets put on the stack first? Open parentheses. That's on the stack. We're now pointing up here. What happens next?
Close parentheses. Well, it pops it.
It pops it because it sees a closed parentheses. So it's going to pop this, basically make our stack empty again, and it's going to compare what just got popped, this, and make sure it's an open parentheses. It is, so it's going to continue forward. All right, so now we're up here. What happens next? Adds that guy to the stack. Going to increment. We're at the closed solid parentheses.
So it pops out.
So we're going to pop this and make sure it's a solid, which it is. So we're still good. Now we go to the parentheses, open parentheses. What happens? Puts this guy on the stack. Increment the stack pointer up here. Move on to the next character. Adds that guy to the stack. Moves him up here. Now we're at
Top one and checks it.
right. So now you're going to check to make sure this guy's a solid open parentheses. He is. So we're good so far. And we're going to check that. Now we're at this, and what do we do?
Pops it out.
Pops him off the stack. All right, and we check to make sure he's an open parentheses. Okay, and we are done. Now, there is actually an error in this code. Does anyone know what it is?
There is the semicolon.
Not up there, no. Good try. Can anyone think of the test case before I write it? I'll give you a hint.
Brackets or curly brackets?
I'm sorry?
There aren't any curly brackets in there?
No, I mean, we could add some curly brackets. Let's put a curly bracket right here. Isn't that balanced? True. That works. Give you a hint. What one character could I put right here that would make the code fail? Actually, there's 3 characters I can put here. What if I put an open curly bracket? Is that balanced? No. Uh-oh, we said true. The last problem was if we did not detect an error, return true. We really should first spell detect correctly, and then return tokens.isEmpty. Right? Because the stack needs to be empty at that point. Because if there's anything on the stack, then it's not balanced. So we need to turn stack is empty. Now if we run it, it'll say false. Okay. How bad was that? Not too bad? I mean, I did it, so of course I made it look easy, right?
Yeah.
Made it look easy. Hopefully you can see that. Well, if you're trying to do this with an array or a linked list, and not use anything that's like a stack, probably would not be too much fun. Can we do this recursively? Instead of using a stack? Let's see. I didn't even think about that until just now. Public static boolean is balanced recursive string. Okay. All right. Well, if we're doing this recursively, what would be the base case? How do we know when we're done? What's the simplest? It's already balanced. Well, what? Yeah. If the expression's empty, if it's null or expr dot equals, we're done, right? Obviously, an empty string is balanced, so we're good there. So we'll just do char c equals expr dot char at index 0, right? Okay. So that's what I'm currently at. And of course the recursive call would be to do is balanced recursive of exp dot substring starting at 1. You know, skip 1 and go over. Okay. But how can we check this? Cursive one's going to be a little trickier.
But it can be done, right?
Yeah, it can be done. I'm actually trying to think of it in my head, the best way to go about it. There's different ways to do this. I haven't decided which way is better. Because if it's the real trick is that if C is an open parentheses or C is an open curly bracket, or C equals open solid bracket, then you want to recurse. You're like, okay, we need to store our last character on the stack. But when we get back from that, that's cute. We basically are done. So what needs to actually happen is balance will return an integer for now. So instead of returning true, we'll have it return 0. And we also need to know our position. So EFPR.size, or I should say position is greater than or equal to what's it, XPR.size. Ooh, that's weird. Dot length. We'll return. Alright, so this is actually going to give us hopefully what the next position is. Hopefully keep track of it. So if we're at an open parentheses, we really need to know what's our next target. So if our next target's a closed one, then we know we're good and we can keep going. Otherwise, we're going to have to use the stack somehow. But what's the stack actually storing? It's storing where we are along. Yeah, where we are along. Can anyone think of how we can do this? No! Not really? All right. This one is pretty difficult, I've just realized. Because you need to get with the open. You get in open ones, and you're actually going to have to keep track of a bunch of open parentheses. And then when it returns, it needs to give you back to closed. Oh, this is going to be evil. No, let's not do this. I'll just type a comment here. Sadness. All right. Anyways, we can also do basic expression evaluation. Does the computer have to do this? Maybe? Yeah. Does it have to evaluate your expressions? So the simplest thing is if it's a 3, you know, a number or a variable x. Okay, that makes it pretty easy. These are expressions. We also have an equal, which is considered an operator. So it's the left-hand side after the assignment has occurred. Good, we still have time. Sometimes you have to evaluate the expression yourself or without the benefit of a compiler. Oh, that'd be difficult. So how can we evaluate an expression such as 1 plus 2 times 3 plus 4 using 2 stacks? Oh, it tells you right there. So you're going to have one stack keep track of the numbers, and another one keep track of the operator. All right. Wow. All right, let's do that. Let's see what we got here. And we'll do evaluate. Pass it a string, like 1 plus 2 times 3 plus 4. Public static void evaluate string expression. All right, so we want to evaluate. Did I misspell evaluate up here? I did. All right. So we need 2 stacks. So one stack is going to be of, what is it going to be, of characters, and that'll be your operators. A misspelled character. Oh, it's string. Equals new stack. And we have another stack of, what's the other one? Make them integers. Okay. Ooh, this is gonna be frustrating. Let's simplify this and say all numbers are single digits. We could, if this was a fully parsing class, we would build a tokenizer which would be able to parse the entire number, determine if it's an integer or a double or a string, and then return that as well as telling you what it is. But we're not writing a compiler here, unless one of y'all wants to write a compiler. Anyone? You're good? You sure?
Sounds like a lot of work.
Yeah, it sounds like a lot. It's actually considered the second hardest problem in computer science, writing a compiler. Just FYI.
What's the first?
Writing an operating system. Number 3 is actually game development, although it's a far distant 3 between It goes 1, 2, long jump 3. All right, so we'll just assume all numbers are single digits. So let's go ahead and do a good old for int I equals 0, I is less than expression. We'll go through all the characters in the expression. So we got a character C equals expression.char at. So here we have the expression, and we have a character. All right. Okay. Well, let's at least set up how we push things. So if, what's it, C dot, ooh, do we have something? No, we don't. Let's go use Google real quick. Java check if digit is a number. Is there an easy way to do this, or are you going to make it hard? We don't want to parse it. All right, fine. So if C is greater than or equal to 0 and C is less than or equal to 9, then it's a digit. So we'll just have integers dot add integer dot parse int of C. Capital I integers, there we go. Oh, it doesn't want to parse it? All right, we'll do it the other way. C minus 0. Ooh, what's that doing?
Oh, is that? What would be ASCII value? So
Yeah,
ASCII value?
right. So you're subtracting the ASCII value to convert it to an integer. Else, we'll do operators dot push. Let's see. All right, so then we push the operator.
Are you going to comment that?
What am I commenting? Oh, yes, thank you. Push the operator. Well, this should, all right. And then compute the integer value by subtracting the ASCII value from it. Okay, thank you. All right, so now we can push all the digits and all the operators. Let's go back to slides because I think they explain it this the best what we have to do. If you see a number, push it on the stack. Good, that's what we did. If you see an operator, while the top of the operator stack holds an operator of equal or higher precedence, pop the old operator, pop the two values from the number stack, apply them to it, and push the result back to the stack. While. Ooh, that's a while. So while the top of the operator stack holds an operator of equal or higher precedence. All right, so let's go create a quick little helper function here. Public static boolean is equal or higher precedence. Character op1, character operator 2. So if op1 is plus, then we can return op2 is equal to plus, or op2 is equal to multiplication, right? Because if your first one's plus, then another plus or another multiplication is equal or higher. But if op1 is equal to multiply, then you just can return op2 is equal to multiply, because only because plus is not equal to or higher. And we'll just stick with the adding and multiplication for now to make our lives easier. Okay. So the question here is, while the top of the operator stack holds an operator of equal or higher precedence. All right. So while we have operators.peak, and we want to say is equal or higher precedence of the top of the stack, and of course our character we're evaluating. So while that's the case, while that is happening, what does it tell us to do? We pop the old operator, pop the two values from the number stack, and apply the old operator to them. Oh boy. Okay. Sounds like we should apply. We'll do operator.pop and then integers.pop and integers.pop. Right, we want to apply the operators to the two integers. Okay, so let's just create a separate function for that to make our lives a little easier. It'll return an integer. I'll be applying character op int num1 int num2. And we'll just do switch on op. In the case of plus, we'll return num1 plus num2. In the case of multiplication, we'll return num1 times num2. And for everything else, we'll just return -1 because something bad happened. System.err.println unknown operator. We'll just say we don't know what this operator is if there's a problem, and then return -1. Okay, so there's the apply. Probably should make it public static apply. And we'll go int new num equals apply, because that's actually applying it. And I'm pretty sure it tells you to pop it, right? I'll push the result on the number stack. Good. Integers.push new num. All right. Okay. And then you push the new operator on the operator stack. All right, great. Okay. Well, that seems fairly straightforward. Except the last thing we have to do is while operators dot is empty. Is empty. I should actually say is not empty. We need to do this whole charade or dance again, because we need to make sure we actually apply all the final operators that we have on the stack. And then when we're done, so right here we're going to apply any leftover operators and then return the final result, which should be on the integer stack. All right. I wonder if we did this correctly. Dot pop. Set as a void. Oh, well, let's make an integer. A little complicated, eh? Yeah. Let's see what happens. I wonder if I see if we did this right. Ooh, there's still an error. What's the error? There's red in here somewhere. Well, we'll just have the compiler tell me. Can't see it right now. Java missing return statement. We'll just return false. All right. Got a good old stack problem. All right. Until stack is empty exception. All right. Stack is empty at this point. So we're basically saying that when you first get the operator stack is empty. So we'll have to say while not operators dot is empty and equal or higher precedence. So let's do that. 21. Is that correct? Let's see. 2 times 3 is 6. Plus 4 is 10. Plus 1 is 11. I wonder what it did instead. Well, let's go ahead and test this a little and see if we can come up with what the problem is. So 1 plus 2. Hopefully that'll give us 3. Hey, it can do that. how about,
7 times 3.
yeah, it's probably doing 7 times 3 is the problem. All right, so that's still good. Now here's, so this should be 6, or not, that should be 7, but it came out 9 because it's doing the plus first. Yeah, so the problem is with our is equal or higher precedence. So if the operator going on top of the stack, wait, operator.peak is equal or higher precedence. So you have num, I think we did this backwards. Yes, we have this backwards. Right, so we have this backwards. So really it's only if op2 is plus, because if you have multiplication, it's not a higher precedence. And then down here is where you would have either. All right. Now that should give us 7 and now 11. I switched the precedence inadvertently. Okay. How about that? Did you like that?
Yeah.
That was great. Does the computer have to do that? Yep. So how would we add variables? It's actually not going to be that bad, I say.
Yeah, just like the recursive. We tried doing that, wasn't that bad.
All right, yeah, at the end performing the remaining operation. So let's actually watch how this is done. Oops. So push 1 on the stack, put a plus on the op, push 2 on the number stack. We're good so far? Multiply, because multiply is higher precedence push and plus and multiplication. You push multiplication on the stack, all right? So multiplication goes on the stack. Put 3 on the stack. Plus, because plus has a lower precedence than multiplication, what happens?
Pops multiplication off and put plus on. And then
It pops, yeah, pops multiplication, and it also pops
plus.
no. You're popping the multiplication, which means you need to apply multiplication. But what else do you need in order to do that?
Pop the number.
Yeah, so now you pop 2 of the numbers and the multiplication, do it, push it back on the stack, compute 2 times 6, push 6 on the stack, and then push plus. So then you have 1, 6, and then the other one just says plus. Push 4 on the stack, and now you're done. So you pop 4 and 6 with the plus to get 10, then you pop 10 and 1, add a plus, and now you get 11. Fun? Mm-hmm. Right, so we could do it with parentheses. When you see a left parenthesis, treat it as a low priority operator and put it on the operator stack. When you see a right parenthesis, perform all operations on the stack until you reach the corresponding left parenthesis. Then remove the left parenthesis. So now you could actually implement a parentheses with this scheme. You ready for that? Variables. There are 2 ways to handle variables in expression. When you encounter the variable, look up its value and put that number on the stack. That sounds easy, doesn't it? But what's implied there? You know what the value is. Yeah, simplifies the stack, everything's a number. When you encounter a variable, put the variable itself on the stack, only look it up, value it later when you need it. This allows you to have embedded assignments such as 12 plus x equals 5 times x. Yeah. Did you know that was legal code?
This is illegal?
Yes, that's legal.
Oh, legal?
Legal.
Oh, okay.
Yeah, you, well, I should take that back. You can do this in C, but not in Java. Why do you think Java didn't want you to do this?
Slightly confusing.
If you could just drop the word slightly or maybe replace it with greatly or extremely. Yes. this gets really confusing, especially if you start nesting these things. Because then you have to keep track, okay, when is X being assigned?
Why would
What's
you want to do that?
It simplifies your code, so you can do everything on one line. And then you can have bragging rights about how your code is compact and no one else can read it, and only you can understand it. In other words, it's a terrible idea. All right, but how do we handle the equals operators? So it's just another one, lower precedence than everything else. It should have higher precedence than the parentheses. Okay, great. So you evaluate the right-hand side and then store the value in the variable on the left-hand side. What would we use to store the value? Because what are we doing? We are, well, we have a variable and we want to store its value. So we are citing. How do we store that in our code? What class would you use? Because we have X and we want to associate X with the value 5. What's that called? Do I have a good one here? We have a variable X, and then we can store a number associated with it. This one we have integer string, but we could just have string integer. So we're mapping. We're trying to map a variable to a number. So we can use a map to store that for us. And that way you can get it from the map as well. Because when you do cars.get on X, it would return whatever you stored, maybe a 5. Stack containing variables, well, that's just silly. But there we go. At the end, two things result in multiple all right, we don't care about the rest of this. Oh yeah, what happens if it's ill-formed? So
wouldn't it try to get the second number?
yes, and it'd be empty, and therefore,
You know?
yeah, you usually want to give you some type of error. So that's why the code I wrote is not fully correct. But because you want to detect if you ran out of numbers, give me an error. Of course, this is not correct either, is it? Unmatched parentheses, same here. Or you may have a variable that has not been assigned. So there's a lot of problems that could happen. But isn't that nice of the compiler to tell you all these things? Do you have a new appreciation? Yeah. Okay.
Now it makes me just want to build one of my own.
Spare time?
Yeah, just crunch away.
All right. I don't care about the rest of this. Stacks in Java. Okay. This is important. We'll go over it again. So you may have a method A. What does method A contain? It has an X and a Y.
Yep, and y equals 0.
And Y equals 0. X is some value. So there's Y. And then it's going to call method B. So method B goes above it with its own Y and Z, setting its Y to 5. Then it returns, which gets rid of Y and Z. And now you're back up here, so you're going to increment Y, which would make Y 1. Okay? Good. Supporting recursion. Didn't we already do factorial? N, if n is less than 1, return to 1. Otherwise, n times factorial. Call it a day. Oh, we can do an animation. All right. Factorial of 3. Here we go. N's 3. R is 1. N is 3. R is put on the stack as 1. Right. Now, part 2. Well, now N is 2. N2 is put on the stack. R is 1 put right there. And now we're going to recurse again for N minus 1. So n minus 1, n is now 1, but we know r is 1, so we put that on the stack, and we find out that n is less than or equal to 1, so we're going to return 1, which is just r. Now we pop r off, and the stack and return 1 is the factorial. Oh, these slides are getting terrible. Oh my goodness. So factorial of when n was 2 is now 1. My goodness. So n, yes. Factorial is 1. We return 2 times 1, which is 2. Return 2. All right, great. Now in 3, we notice that this factorial of n minus 1 was 2, so we got that from up here on the stack, and now we're going to multiply by n, which is 3, which makes it 6, and then we pop it and we return 6, and we're done. Everyone good with the terrible slides that I've drawn on the board? That was beautiful. Note to self, fix this for next time. We don't care about stack frames. We've talked about generics so much, we're done with them. Summary. So stacks are actually pretty useful for solving particular problems. Hopefully you can see that if you're trying to solve a balanced bracket problem and you didn't use a stack, it might get pretty complicated pretty quickly. Stack simplified that a lot. Good for any type of arithmetic operation or expressions, nested statements, any sort of nested data. All right, great. Any questions about stacks before we go to your lab? So the stack is last in, first out. What other type of data structure do you think there is?
First and last out.
First in, isn't that also a stack? Because the first one in would be the last one out.
Oh, probably one that deals with inserting into the middle of the stack.
Okay, yeah, we could do that. But if it's not last in, first out, could it be first in, first out? What would that be? A what? A list, kind of like a list. Well, you do this all the time, probably every day. When you go get your food, is it the last person in line comes out first, or is it the first person in line?
Sometimes it can be. Sometimes people get their food before you, and then you're just like, well, I ordered first. Why haven't I got mine?
You don't tackle them and
No.
dispense them just.
Yeah.
All right. Right. So that's called a queue, but we're not going to talk about it.
Yeah,
They have a queue, right?
Always.
We're not going to do a queue in this class, but you will when you go into data structures. But I think a stack is really important. All right.